Hi everyone. So we are now going to look at molecular elements and compounds. In chapter 2.1, you looked at ionic compounds, and those are composed of metals and nonmetals. And a molecular compound is a pure substance composed of molecules made up of two or more nonmetallic elements. And a covalent bond is a bond that results from the sharing of at least one pair of electrons by two atoms. So for example, if we looked at hydrogen, H2, we would draw the Lewis diagram of one hydrogen atom. And so it has one valence electron. And we would draw the Lewis diagram of the other hydrogen atom. So when you learned to draw a Lewis diagram, you learned that you would put the dot at the top, the electron at the top. But when you were showing bonding, you are free to move electrons around. They are not held in space, and you will find it easier if you move them around to show that they're pairing, because that's what happens. When two electrons come close to each other from two different atoms, they will bond together. So we call these, consequently, the bonding electrons. I know that's shocking. Bonding electrons. Now, so why does hydrogen only need two? Well, remember that hydrogen is in the very first row of the periodic table. So when it has a full shell, it has two, just like helium. Okay, so it's the only one that would bond like this. It's a very special element and often is grouped on its own. We call this diatomic. Okay, diatomic, and perhaps you learned about this before. The diatomic elements. We have a number of them that are diatomic, and maybe you learned about Hofbrinkel the clown. So Hofbrinkel, HOF, bromine, iodine, nickel, and chlorine. So those are the elements that always will exist in pairs. Hofbrinkel. And I'll just draw a little clown here to remind you. Okay, no judging my clown. This is my clown. Okay, there's my little clown. Happy face. Happy clown. Okay, Hofbrinkel the clown. Okay, so fluorine is also another element that is diatomic. So when we draw fluorine is in column 17. So it has 7 valence electrons. And again, I'm going to break the rule about where we put them, because if I was doing it the way that you were taught to do it, you would end up on this side, right? I mean, you were shown to, I'm going to show you. Remember, 1, 2, 3, 4, 5, 6, 7, and there's that last one. But I'm going to flip it to the other side so that it's easier to bond with another fluorine. Just makes my diagram look neater. So this one I will draw like that. 1, 2, 3, 4, 5, 6, 7. So in the middle, that circle around the oval, actually oval shape shows that they're bonding. Okay, bonding. Now, how many valence electrons now does each fluorine have? Well, the 2 in the middle count as for each of them. So 2, 4, 6, 8 for that fluorine on the right, and 2, 4, 6, 8 for the fluorine on the left. Okay, so those are your diatomics, a couple examples. Now, when we're looking at forming covalent bonds, we look at the bonding electrons, and those are the electrons that are available in the valence shell to form a covalent bond with another atom. And it varies with the group number. So there's a pattern for this. So if the element's in group 1, okay, it's going to have 1 valence electron, has a bonding capacity of 1 valence electron. So for example, just like we did up there, that is hydrogen. Okay, hydrogen and hydrogen only. If we look at group 14 has 4 valence electrons. It'd be handy if you're looking at your periodic table as we do this, so you can reference to see what that looks like. So open up to your periodic table, or find one on your phone or what have you, and you will see that, and I'm going to grab mine. Find one close by. Doesn't appear that I have one. I do. Just give me a second. I'm going to find my periodic table. Oh, got my textbook. So in case you're not making the connection to valence electrons in the periodic table, some of you this might be easy for you, but others you might need to have a visual. So let's have that visual. So, right, here's our periodic table. Here's hydrogen, first column, 1 valence electron. Column 14, zipping across, and I end up at, top guy is carbon, okay? So if it's column 14, right, that means that I'm 1, 2, right? 1 valence electron, 2 valence electrons. I'm trying to show that, yeah. 2, sliding over, 3 would be boron, and 4 would be carbon, okay? So that's how that works. So carbon has 4 valence electrons, so therefore has a bonding capacity of 4 because it wants to get to full valence shell, which would be 8, okay? Column 15 then would have 5, and that means it has a bonding capacity of 3. Well, how does that work? Well, let's look at the element we're going to talk about from column 15. That would be nitrogen, right? So nitrogen has 5 valence electrons. So let's draw nitrogen. So nitrogen has 1, 2, 3, 4, 5. So that means it has 3 spots where it can bond with another element, okay? Moving along to column 16. So naturally we'll talk about the next guy in the top row, which would be oxygen. It has 6 valence electrons. So oxygen, 1, 2, 3, 4, 5, 6. Again, this bonding capacity, how many electrons are all alone? It has 2 spots for bonding. And lastly, column 17, at the end of that row, we have fluorine with 7 valence electrons. So we'll draw that one. 1, 2, 3, 4, 5, 6, 7. 1 spot for bonding, bonding capacity of 1. Okay, so you're going to read more about this in 2.3, but we're going to talk about it now because it's important for telling us the type of bond that we're going to be dealing with. Because so far, all we know is if it's ionic, it's a metal and a nonmetal. If it's covalent, it's 2 nonmetals, right? So that is the best way to look at the elements in question, is to determine what type of elements are involved. Sometimes it can be tricky if you have there's 2 types of covalent bonds we're going to look at, polar and nonpolar. So how do we know which one it is? We have to look at what's called electronegativity. So if you remember back to periodic trends, we talked about electronegativity, and that was one of the trends, right? So that was the ability of an atom to attract bonding electrons to itself. The ability of an atom to attract bonding electrons to itself. So for our purposes, it's a continuum, and there is debate about it. You can look it up in various textbooks and online, and you'll see all kinds of different numbers. But in essence, really a pure covalent is only 0, because that means an equal sharing of electrons in a bond. It's the only way if it's 100% equal if it's 0, because that means the difference between them would be 0. Okay? So we are going to use 0 for our purpose of defining a covalent bond, and that's what it says in your textbook, so we're going to stick with that. But you might see other things, so for our purposes it will be 0. Between 0 and 1.7 is a polar covalent bond, and greater than 1.7 is ionic. Your periodic table also has these values, okay? You also can see a chart of them, and you might see various different charts. Use whatever information's in front of you. For our purposes, use mostly your periodic table. We will. So this is right out of your textbook, and it's showing electronegativity values. Hydrogen is 2.2, carbon is 2.6, nitrogen is 3.0, oxygen is 3.4. What does all that mean? Well, think about the trend on the periodic table. Electronegativity means the ability of an atom to attract bonding electrons to itself. So the more electrons it has, the higher the electronegativity. So if you remember from periodic trends, that increases to the right and up, okay? So if you look at these elements, so I'm going to bring up my periodic table here. And you notice that some of the values are on here. Look what's happening. 2, 2.6, 3, 3.4, 4. Look how electronegative fluorine is. The most electronegative atom because it's really tiny, has 7 valence electrons, so it's pulling all those electrons towards itself in a bond. Okay? So, how's that going to help us now? Because we're going to talk about different types of bonds, covalent bonds. So, this shows you a picture of a bonding continuum. And what does the bonding continuum tell you? Well, it tells you that the type of bond you have when your electronegativity changes, right? So it's a scale. So if you see, it goes from 0, pure covalent, all the way to a high number, which would be ionic, okay? And this here is showing you what's happening inside the bond. Here we have nonpolar. Notice, this is an equal sharing of electrons. Here we have a polar covalent bond, and it's shown by these little neat little symbols here. You're going to learn about those in a second. Those are called deltas, okay? Deltas that show us we have a polar bond, negative side and a positive side. That little hand in there is not supposed to be there, but anyway, just ignore that. And then when we get to ionic, these are charges. So in an ionic bond, you have a positively charged side completely and a negatively charged. Those ions exist together in a bond, it's called, but all these variances in bonding determine their properties, which is, you know, really the crux of what we're trying to get to and understand is the difference in the properties of ionic and covalent and polar covalent bonds. Okay, so there's a bunch of stuff here for you to write down, which make sure you might have to rewind a couple times or pause it as you copy. So we've got covalent bonds. Those are two nonmetal atoms try to complete their valence orbit, fulfill the octet rule by attracting valence electrons from the other atom. Neither atom is strong enough to remove the electrons from the other, so the electrons end up being shared between the two atoms. So that's kind of what's key here. And if you look at covalent, co kind of means sharing. Valent is your valence shell, right? So that's how that really works. Valence shell. The valence shells overlap and share the electrons. Okay, so like hydrogen and hydrogen beside each other. So let's say this is their shell. You've got this one, it has an electron, this one has an electron. And oops, those electrons should be in the middle there. Let's just fix that. So there should be in the middle of that little sherry thing I drew. Let's just get rid of that electron where it shouldn't be. So in the middle there, those are the electrons being shared as their valence shells overlap. Of course, that's just a diagram, but to kind of get the idea and understand it. So if we can take these electrons and turn them into dashes. And a dash represents a shared pair of bonding electrons. If you have one dash, it's single. Okay, so that means like this is equal to a line between the pairs of atoms. If you have a double dash, it's a double bond, two shared pairs of electrons, so it would be like this. 1, 2, 3, 4 equals 1, 2, and a triple would be a triple bond. So it would look like this, 1, 2, 3, and that equals 1, 2, 3. And we'll see some examples of that in the following molecules we're going to draw. Okay, so we have a nonpolar bond. That's the first type we're going to look at. And in a nonpolar bond, we have an equal sharing of bonding electron pairs. There's no electron transfer, and the electronegativity difference is 0. So we have a couple examples. I will draw chlorine and oxygen. So let's draw chlorine. So chlorine has 7 valence electrons. And so we've drawn 2 of them beside each other. Let's check something here. Well, we did fluorine before. I'm trying to remember which one we did. So chlorine would have, because it is 7, these 2 in the middle are going to share, and they're going to form a single bond. and the electronegativity difference is equal to 0. Why? We call this delta En is equal to, let's say, Cl minus Cl. Actually, we should say delta En of Cl. Okay, so let's look up the value just to show that we've written it down. You're going to see some that are going to be different soon. So going back to my chlorine in my periodic table, 3.2 is the value. Okay, so if you have two 3.2s, 3.2 minus 3.2 minus 3.2 is equal to 0. Okay? All right, oxygen. So let's draw oxygen's Lewis diagram. 1, 2, 3, 4, 5, 6. And I'll put another one beside it. 1, 2, 3, 4, 5, 6. So I look to what's unpaired and I pair it up. So I've got a pair here and a pair here. Okay, so is this correct? You got to count. 2, 4, 6, 8 on the right oxygen atom, 2, 4, 6, 8 on the left. So they both have 8, so everybody's happy. So 1, we can replace the electrons with lines to show the bonds, and our delta En is equal to 0. So delta En is equal to, I put this line here that means absolute value. Remember that from math class, that means no matter what number's in there, we don't make it negative. So delta En of oxygen minus delta En of oxygen. Let's find out what oxygen is on the periodic table. And it's 3.4. Okay? I didn't really point out how I knew that because I kind of forgot to mention it, but look at your legend on your periodic table and it'll tell you what number is what. So that I knew that the number right under the atomic number is the electronegativity. Okay? So check on whichever periodic table you're using and that's how you'll determine it. So we said 3.4. Slide this up a little bit. So 3.4 minus 3.4, and of course that's equal to 0. Okay, so that's a nonpolar covalent bond. Okay, moving on to some more nonpolar bonds. Got a couple more examples for you. We have, well, let's just talk quickly about shape before I do that actually. Just because you're going to see some and I want to be able to be familiar with a few. The shape of this, and we're only going to talk about a few, is linear. Why is it linear? Well, because it's a line, right? Straight across. So it's a linear shape. You'll have to get to recognize a few shapes. All right, nitrogen now. Let's draw that one. So nitrogen has 5 electrons, and I need another one beside it. Now this one, no matter how you do it, you're gonna have all kinds of little circles everywhere when you start matching up your electrons. So I'll match up these two, then I match up these two, and then these two, I gotta match them up. Wouldn't matter which way I do it. There's no real neat way to do it. Kind of looks like a little smile, doesn't it? 2 eyes, a nose. So we can count to see, does each atom have 8 electrons? 2, 4, 6, and 8, and 2, 4, 6, 8. So everyone has 8. So good, this is all done. So I put 1, 2, 3. Nice and neat that way, isn't it, when you do the lines? And again, what we call this? Linear. And our delta En, I'm not gonna calculate this one, I think you get the idea, is equal to 0, okay? Because it's the same atom. All right, last one, pH 3, a little bit different. So how are we gonna draw this? You always put the one with the most electrons in the middle. I'm going to show you some tricks in a bit too, but just this is one of them. You have to put the one with the most electrons, and that'd be phosphorus with 5 electrons. And then you place the other ones around it. So we got 1, 2, 3, and every hydrogen has 1 electron. So put a little circle around those electrons. So we know hydrogen's happy because it only needs 2. So 2, 4, 6, 8, phosphorus has 8 now too, so it's also happy. So we have P, 1, 2, 3, H, H, H. All right, so now let's check the delta EN of this. This is not the same elements. I should actually put OO here. You only need to check one. So phosphorus and hydrogen. Let's check it out. Phosphorus is right here, 2.2. Hydrogen, also 2.2. Okay, so that's obviously going to be equal to 0. So we'll just write that out. Delta EN of phosphorus minus delta EN of hydrogen, and it's 2.2 minus 2.2 equal to 0. So again, non-polar, no poles. Now, polar covalent bonds, next type, these ones have an unequal sharing of bonding electron pairs or pair. There's no electron transfer, and now we have an electronegativity difference between greater than 0 and 1.7. All right, so, shape of this one, the shape of this guy. We call this one trigonal pyramidal. Special name, trigonal pyramidal. All right, so hydrogen and chlorine. So hydrogen has 1 electron and chlorine has 7. So I could have put this on this side to make it easier. I'm gonna do the bonding. And so I have 1 bond. And it looks like this. Now, what about my delta EN here? So I say delta EN, HCl, delta EN of H minus the delta EN, oops, shoot. Whiteout's a good thing. And then let's look that up. So we know H is 2.2, we already saw that, and Cl is 3.2. So 2.2 minus 3.2 is equal to 1.0. Therefore, this is polar, right? Therefore, polar covalent. And the shape of this would be linear again. Okay, all right. And how about this next one, carbon dioxide? Carbon dioxide. So we have carbon. Which one has more electrons in this case? Would be our bonding capacities. Actually, it's not necessarily electrons, it's how much bonding they can actually do. So this one has 4 electrons and oxygen would have 6, but it only has a bonding capacity of 2. So let's put one on one side. And so how did I decide that? Well, when you're drawing something and you want the electrons to be shared, put them towards or close to another one that will be able to share. So I put my 1 electron on close to the one on carbon and one on the bottom. And this time, so those 2 are gonna be taken up. So I'm gonna put my 1 lone electron here, so it's close to that, and my other lone electron here, so it's close to that one, okay? But they both still have 6. If you do it wrong, you'll get the idea once you start practicing it, okay? It's something that may come with time for you. Just be patient, you will get it. Okay, so here's the bonding part. So we bond these 2 electrons, okay, these 2 electrons, and these 2 electrons, and these 2 electrons. So that's why I positioned them the way I did. All right, so now we count to make sure everybody has 8. So we've got 2, 4, 6, 8. That oxygen's happy. The carbon has 2, 4, 6, 8. It's happy. And this oxygen has 2, 4, 6, 8. Everybody's happy. Let's draw it with lines. Much neater. So we got 1, 2, 3, 4 electrons. Line, line, carbon. Line, line, oxygen. And then it doesn't really matter where you put these pairs. They're moving. They're never going to be sitting still. So we say this, we got to find the delta En to see what kind of bond it is. Delta En, oxygen carbon, is equal to, doesn't matter if you do oxygen carbon or carbon oxygen, no, as long as they're both there. And remember, it's an absolute value anyway. So that would be oxygen is 3.4. Where are you? 3.4, and carbon is 2.6. Okay. 3.4 and 2.6, and that is equal to 0.8. Okay. 0.8. So we know that this is also a polar covalent. Now I forgot something integral in the last one, so I got to remind or do it for this one and the last one. Because they're polar, we have to show the polarities. We have to show where the electrons are actually going to go. So where are they going to go? Well, if we look at this bond here, right, which one has the higher delta En? It's oxygen. So electrons are going to be pulled to this way towards the oxygen in the bond. So we would just show, if I could just show that actually the electrons are going to go that way, and this is going to be negative. That's my little delta. Electrons are going to go this way, and this is going to be negative. That's my other little delta. So this carbon is going to be slightly positive, and that's what the delta means. Slightly means slightly charged. Slightly charged. That's what delta means, okay? What would we do for hydrogen and chlorine? Well, chlorine clearly has all these electrons, so we can just look at the number, but we can just look at how many electrons it has and say it has a higher delta En. So electrons are going to be going this way. So this is going to be the negative guy, and this is going to be the positive guy. Okay, that's what you need to do. So if it's polar covalent, you must show the charges. If it's non-polar, don't show any charges. Simple, right? All right, the last one we're going to do of these examples is hydrogen cyanide. Oh, and the shape of this guy is also linear. Linear, okay? Pulled straight across by those double bonds. So which one has the highest bonding capacity here? Well, you can draw this one as written because it shows you carbons in the middle, and that's exactly how it is. Carbon goes in the middle with 4 electrons. Hydrogen has 1, and nitrogen has 5. So if I do a bond here, just to show that that electron's gone, I need 3 more bonds, which of course nitrogen can provide. So where would I put my single electrons? You got it, 1 at the top, 1 at the middle, and 1 at the bottom. And the nitrogen has its little lone pair at the side, right? I could put them the other way, but then it's just gonna look messier, so it's up to you. As long as you understand it, that's what's important. So 1, 2, and you're clear in your diagram. 3, there's my 3 bonds. Count, is everybody happy? Nitrogen has 2, 4, 6, 8, yay. Carbon has 2, 4, 6, 8, yep. And hydrogen has 2. So let's draw it with just lines. H, C, 1, 2, 3, N, and a lone pair. Isn't that pretty? So in this case, we're going to calculate the delta En of this bond and this bond because there's 2 different types of bonds here. Carbon and nitrogen. So do I have a carbon here? Yep. Carbon is 2.6. Carbon, delta En of nitrogen. So 2.6 minus, I don't think I had nitrogen yet. So I gotta go look nitrogen up. Nitrogen is 3.0. 3.0. So that's equal to 0.4. So that's that's polar. And then let's check the carbon hydrogen. Oops, delta En, carbon, delta En, hydrogen. So carbon was 2.6 and hydrogen is Where's my hydrogen? 2.2. That's also equal to 0.4. So they're both polar. You can just put in short form, therefore PC, polar covalent. It's not President's choice, LOL. All right, so where are we gonna put our charges here? Think about it. Which one has the biggest delta EN? Biggest number, nitrogen. So this guy's gonna be really negative. This guy's gonna be a little bit more negative, a little less negative, and then this hydrogen is gonna be positive. So electrons are being pulled in this direction. They're all going that way. That's how the electrons are moving. And again, this would be linear. Okay? All right. So what are some properties then of covalent bonds? So because of the type of bonding, they can exist as gases, liquids, or soft solids at room temperature. Remember that ionic compounds were crystals, right? They weren't forming these different states. And they have relatively low melting and boiling points because the bonding isn't as strong as ionic, right? They exist as molecules instead of ions. And because of that, they do not conduct electricity, right? We know that you need an ion to be able to conduct an electrical charge, okay? And they do not readily dissolve in water as well. So that makes them very, very different than their ionic counterparts. I'm gonna try to put this up a little bit. Okay, so I'll let you take that down for a minute. I need a bookmark here. I need to hold on to that. So take a minute to copy that. And then I'm going to show you how to draw some more Lewis structures of molecular compounds for some more challenging structures. It's kind of a method. Okay, so I'm going to do this in a separate video just to give us a bit of a break here and break up this video. So I'll meet you back in a minute to draw Lewis structures for molecular compounds.